Hello students, welcome you all. In my today's lecture, I will start carbonyl compounds. So in this lecture, I will tell you the introduction about the carbonyl compounds, what are carbonyl compounds, what type of reaction it will undergo, and what are the factors which affect the reactivity of carbonyl compound and the acidity of alpha hydrogen atom in the carbonyl compounds. So in my previous lectures already I have discussed about the substitution reactions in alkyl halide, elimination reactions in alkyl halide, about the alcohols and so on. So let us give you some idea about this carbonyl compound in this lecture, introduction about the carbonyl compound. Now this carbonyl compound, all of you know, so this is one of the functional group and that can be written like this. And this functional group, you can find it in a aldehyde, you may find it in a ketone, we may find in a acid, we may find in a amide, we may find in a dicarbonyl compound, esters, like this. So this all functional group, this contains this carbonyl as a functional group. Now in this functional group, carbonyl functional group, if you see this oxygen is quite electronegative in nature. And the electronegativity of this oxygen, this is approximately 3.5. Whereas the electronegativity of this carbon, the electronegativity of this carbon, this is approximately 2.5. Now, as the electronegativity difference is very high electronegativity difference, so here this bond, this double bond is quite polar in nature, and this is the dipole moment is towards this oxygen being the highly electronegative, and this carbon is comparatively very less electronegative. That's why this oxygen, it bears the partial negative charge, whereas this carbon it bears the partial positive charge. Now here at it bears the partial positive charge. That's why at this carbon, the one of the, or this one is the electrophilic carbon. We can say here it is deficient one, electron deficient, but that's why this is the electron deficient carbonyl carbon. This carbon is the carbonyl carbon. This oxygen is called as the carbonyl oxygen, and this carbon is electron deficient in nature. This carbon is electron deficient. And this is one of the electrophilic carbon. That's why, or we can say this is electrophilic in nature. And the nucleophile can easily attack over it, and nucleophile can attack. So one of the reaction that this carbonyl compound that it undergo, that is the nucleophilic addition reaction. So that's why in carbonyl compound nucleophilic addition reaction is quite common. So nucleophilic addition reaction. Suppose if you have a carbonyl compound and this in presence of a nucleophile, suppose this is the nucleophile, then no doubt the nucleophile will attack over this electron deficient carbon, and this pi bond will break and the electrons will go into the anti-bonding molecular orbital. And what you can write, the oxygen here, it will be at the minus charge, and this nucleophile will add over here. So what type of addition you will see here? So suppose I give this oxygen as a number 1 and this carbonyl carbon as a number 2, then this addition is called as a 1,2 addition. This addition is 1,2 addition. Okay, this addition is called as 1,2 addition. Now suppose if this nucleophile is very, say, strong in nature, it's a quite strong nucleophile. So nucleophile, suppose it is a strong one, and for example I write suppose hydride ion which is coming from lithium aluminum hydride, or hydride ion which is coming from sodium borohydride. So it is giving, this gives the hydride ion, and similarly suppose Grignard reagent giving nucleophile, suppose this is CH3 minus, or this one giving CH3. Now, okay, so in this way, these are giving the nucleophile, and nucleophile, they are quite strong in nature. So quite strong in nature. So that's why here what you have got here, this is the one of the alkoxide ion which is formed over here. This is the alkoxide ion which is formed. Alkoxide ion. So comparatively, if you will see, and this is giving you the weak conjugate base. So here this is the strong one. This is a strong nucleophile is giving you the weak conjugate base. Comparatively, the weak conjugate base is formed over here. This is the weak conjugate base is formed, or we can say a stable base is formed. Stable base is formed like this. Comparatively, the stable base is formed in, if you compare it with this nucleophile, it is weaker one. So that's why the reaction which will occur here, this is forward reaction, would be much higher in comparison to the backward reaction. So this is not the reversible reaction that we can see. Now suppose if we have another reaction, now so this may further undergo this hydrolysis, it may further undergo hydrolysis, okay, and we may get OH over here, and nucleophile will get attached over here. Now suppose if we have another case where the nucleophile is, suppose nucleophile is a moderate one. Nucleophile is a moderate nucleophile, and compared to this one, if it is a moderate one, like suppose it is our hydroxide ion, cyanide ion, or it may be some neutral nucleophile like this. This is a neutral nucleophile. Then in this example here, if you will see, then the product, a nucleophile which is attacks over here again, and the product formed, similar product would be formed, but this product, in this case, the backward reaction, the forward reaction, in because this is a moderate nucleophile, the conjugate base which is formed over here and the nucleophile, the strength is comparable one. Both is the comparable strength between this alkoxide ion as a weak conjugate base and this nucleophile. Both is the comparable one, both is a moderate one. That's why under these nucleophiles the reaction is the reversible reaction. So this is reversible reaction, this is reversible one, this is our irreversible one, we can say. This is irreversible one. Okay. Now there are some reaction where the reaction may go in a backward direction. Now suppose if we have another example where the nucleophile is a weaker one. The nucleophile is a weak one, weak nucleophile suppose, and suppose chloride ion, the weaker nucleophile. Okay, suppose this is a chloride ion, and this chloride ion, it will attack over this electron deficient carbon, and this will go over here. Now we know that this HCl being a very strong acid, and its conjugate base is a weaker one, and it will act as a weaker nucleophile over here, and here this will go in a backward direction much more. Why? If you see here, then this is the O minus which is formed over here, and Cl. Now in next step what will happen? next step, the chloride, and we know that this chloride ion is a very good leaving group. Chloride ion is a very good leaving group, so it will restore, double bond is restored, so that the chloride ion can leave out. So that's why the reaction is very much possible in a backward direction in comparison to the forward direction. So this is about the reversible or irreversible nature of this carbonyl reactions or nucleophilic addition reaction in the carbonyl compounds. Now, what are the factors which affect the reactivity of this reaction or nucleophilic addition reaction? Let us see. Now, so this is what I have told you, one thing, and these are the examples of 1,2 addition. Now, suppose if we have alpha beta unsaturated carbonyl compound. If we have alpha beta unsaturated carbonyl compound. Now, so here in presence of nucleophile, what type of reaction that will take place? Now, one thing what I have told you, usually 1,2 addition takes place. In this case, 1,2 addition. If 1,2 addition takes place, means this is first, this is our second one, and nucleophile will attack over here and so this is our alpha carbon, this is alpha 1, this is beta 1, so that's why it is alpha beta unsaturated carbonyl compound. This is alpha beta unsaturated carbonyl compound. Okay. Now here if 1,2 addition takes place, means over here nucleophile will attack, and here finally H plus may come. So the product here that we will see, the product, finally the product would be, this would be the product in this case. Okay. Now, so it may also undergo the 1,4 addition. Nucleophile, if we have a nucleophile, then 1,4 addition is also possible. 1,4 addition is also possible, and this 1,4 addition, how? Means if this is first, this is second, then this carbon is having third position and this carbon is having the fourth position. So the nucleophile may attack over this position at electron deficient. This is may also act as electron deficient center via this resonance. This may also act as electron deficient center. This is one of the electron deficient center. This may also act as a electron deficient center. So no doubt here this would be the thermodynamic product, and 1,4 addition product that is formed is the kinetic product. So here what you can get, the product that I will get over here, that would be the case like this. So nucleophile will add, at this fourth position. Here the nucleophile adds over the second position, here the nucleophile is adding over the fourth position. So this is an example of this 1,4 addition, or it is also called the conjugate addition. This is also called as the conjugate addition. And here this is the thermodynamic product which is formed, quite a stable one. And this is the kinetic product which is formed. So this is no doubt, this product will be formed very fast. This would be slow product. Why this is fast? Because as you can see, the nucleophile can attack over here easily, and here this one is the much hindered side, but it is giving the stable one. This is the hindered side. This is the less hindered side. So the nucleophile can attack easily. Nucleophile can attack much more easily at here. So this is gives you the kinetically favored product, much faster product, and this is the thermodynamic product. Okay. Now, so two type of addition, that is 1,2 addition. If we have alpha beta unsaturated carbonyl compound, it may undergo the carbonyl compound may undergo the conjugate addition or 1,4 addition may also takes place. Now, what are the factors which affect the reactivity of carbonyl compound? So let us see factors affecting reactivity of carbonyl compound. Factors affecting the reactivity of carbonyl compound. Now, the first factor, the presence of electron withdrawing or electron donating group. Now, suppose if we have electron withdrawing group, then electron withdrawing group, it increases the reactivity. Here, if electron withdrawing group, reactivity increases. How? But I will tell you the reactivity and electron donating group, reactivity decreases. Why? Because electron withdrawing group, it makes the carbonyl carbon more electrophilic, because it makes carbonyl carbon more electrophilic or electron deficient, whereas here, because it makes the carbonyl carbon less electrophilic. Simple one. Now suppose, for example, if we have the example, then now, so which will undergo the higher reactivity? 1, 2, 3, 4. So no doubt, if you will see here, this is the electron donating group. This is the electron donating group. That's why it will reduce the electrophilicity of this carbon. If electrophilicity of this carbon reduces, then nucleophilic attack, that will become not become easier. Okay. In the same way, here it is neither electrophilic, neither electron donating, neither electron releasing. What about this? This is electron. This is our electron withdrawing group, and this is much stronger electron withdrawing group, CF3. So here it will withdraw the electron and makes this one more electrophilic, and this will withdraw more electron. It will make electron much more. So that's why the reactivity, highest reactivity, because here the electrophilicity of the carbon is the highest. That's why reactivity is highest in this case. So this is the highest reactivity, this is the lowest reactivity. Now suppose what will happen if any sterically hindered group is present, bulky group. So presence of bulky group decreases the reactivity, of carbonyl carbon or carbonyl compound. So suppose if you have a bulky group, now here, so if you will see here, this compound is having at this alpha position, at the alpha carbon, the two bulky group tertiary butyl groups are present, which are the bulky group. So due to this bulkiness, the nucleophile cannot easily attack at this electrophilic center. Here two tertiary methyl butyl group is present, one butyl tertiary butyl group is present over here, methyl, and here no bulky group is present. So that's why the reactivity, it is most reactive, this is least reactive. This is least reactive, whereas this is most reactive in nature. This is most reactive in nature. Now, third factor that you will see. The third factor is, suppose if you have acid catalyzed reaction. So acid catalyzed reaction increases the reactivity. Acid catalyzed reaction. So if we have acid catalyzed reaction, then the reactivity of this carbonyl compound increases. It makes the electrophilic center more reactive. So in presence of this acid, this oxygen will get protonated, and this one will get protonated like this. Or better to write it. And in next step, the nucleophile can easily attack over here, so that this positive charge get neutralized. What you will get? You will get here okay. So first of all, in this carbonyl compound, if you will see, then here this carbon center is sp2 hybridized, or this carbonyl compound is a planar one. So if this is a planar one, if this plane, then this nucleophile either it can attack from the up position or from the down position. The nucleophile can attack from the either position, and after that this sp2 hybridized carbon, that is converted into the sp3 hybridized carbon. So here what kind of compound this is? Carbonyl compound. This is a planar one, or we can say trigonal planar, and this is tetrahedral in nature, sp3 tetrahedral in nature. Okay, so as it is a planar one, that's why either the attack, maybe the nucleophile can attack from the upside or from the downside, or we can say, and finally we will get this tetrahedral type of product. Now, so next thing, so this is about the factors which affect the reactivity of carbonyl compound. Now let us discuss the acidic alpha hydrogen atom in the carbonyl compound. Now see this acidity of alpha hydrogen atom in carbonyl compound. So acidic alpha H in carbonyl compound. So suppose if we have a carbonyl compound, and here if you will see, then this is our alpha carbon atom, this is also alpha carbon atom, this is the beta carbon atom, and further it may have the gamma, delta, epsilon carbon atom. Now the hydrogen which is attached to this alpha carbon atom is the alpha hydrogen atom. In the same way, the hydrogen which is attached to this alpha hydrogen atom is also the alpha hydrogen atom. Now in presence of suppose any base, so base, and suppose 0 degrees Celsius temperature, suppose solvent is THF or some of the aprotic solvent, because protic solvent, it may disturb this nucleophile. So it may occur in presence of some tetrahydrofuran as a aprotic solvent. So this base, it will abstract this alpha H, and the negative charge will come over this carbon atom. Now what you will have now? You will have one of the hydrogen atom already present, and you will have a negative charge over here. Now finally, as this is the carbon ion which is formed over here. This is the carbon ion which is formed. This carbon ion, as you can see, and this is resonance and stabilized, and you will get a negative charge over here, negative charge, and double bond at this position, and like this. Okay, so this you have got. Now, so what is the name of this ion? This is the carbon ion which is formed, negative charge over the carbon atom, and here, and this is the enolate ion. This is called as the enolate ion. Enolate ion. Okay, and this enolate ion is more stable than this ion. This is more stable, and this is less stable. Why? Because the negative charge here, it is present over the more electronegative oxygen atom. Here the negative charge is present over the less electronegative. It is present over the less electronegative carbon atom. So if negative charge is present over the more electronegative atom, then it is more stable. And so no doubt, so these two ions which are formed over here. Now if you will see, then if same reaction takes place in presence of some bulky base, suppose if we have LDA and at 78 degrees Celsius temperature and THF as a solvent, then lithium diisopropyl amide. So this lithium diisopropyl amide, this is a bulky base. Now in this case, the product which is formed, or the remove, here the base has taken out the hydrogen or alpha H from this position. Now this LDA, if it is there, then it will take out the alpha H from here. It will take the alpha H from this position. So two alpha H are present, either this one or this one. LDA will take out the alpha H from here, and this will take the alpha H from here, and it will negative charge like this. Okay, so you have this. Now this can also undergo the resonance stabilization, and you have enolate ion like this again. You have an enolate ion. Now out of this two enolate ion, if you will see the two enolate ion which are formed, which is more stable? Now this is more substituted, this is less substituted. So this is more, out of these two, no doubt it is more stable, this is less stable. But if you will see these two, if you will compare this to one, then this is less stable in comparison to this is less substituted. This is less substituted, and this is more substituted. This is more substituted, and that's why out of these two, this is more stable and this is less stable. And so here the product which is formed from there, that would be the thermodynamic product. This will give you the thermodynamic product, and here the product that you will get, that would be the kinetic product. And we know that the kinetic product which are formed are faster formed, and they are formed very slowly. So another thing that we may understand here, why they form fast, because here this being the bulky base, it will take out the alpha H from this less hindered position. So attacks at less hindered position. So this attacks at less hindered site, whereas this attacks from more hindered site, site. So that's why this will give you the slow, this product which is formed is a slow product, thermodynamically stable, and this forms the faster product, that is the kinetically stable. Okay, so and finally we suppose if any nucleophile is present, if suppose any electrophile is present, then this electrophile that can electrophile, in presence of this electrophile, what will happen? And the electrophile that will attack at this position, the electrophile that will attack at this position finally. So here the electrophile will get attacked. In the same way, the electrophile final, the product that you will get after this electrophilic attack, you will get the electrophile at this position. Okay. So this is about the alpha hydrogen atom. Now suppose in the same way, if you have one of the example, then you may easily write the product. In this case, suppose, so if you have the example, then this is the carbonyl compound. What would the product if we have any strong base sodium hydroxide in presence of THF as a solvent and 0 degree Celsius temperature, and this LDA at 78 degrees Celsius temperature. So no doubt what I have told you, this LDA it attacks from the less hindered side, OH minus attacks from the more hindered side to get the thermodynamic product. So alpha H, so this is the alpha carbon atom, this is also the alpha carbon atom. Hydrogen which is present over here, that is the alpha hydrogen atom. Hydrogen which is present here, that is the alpha hydrogen atom. This will attack over here and will get the finally enolate ion, and this LDA will take this one and will get this one. So here the product that we will find, the product and finally any, if you have any electrophile, then electrophile can attack over here like this. Okay. Now if you see some of the reactions, nucleophilic addition reactions, suppose if you have a carbonyl compound, any suppose ketone is there, then in presence of aqueous acid and this one, and what would be the product in this case? So how you will write? So in the first case, so this is a strong nucleophile, and no doubt forward reaction would be more in comparison to the backward reaction. So it will attack and you have this minus charge, and here we will have this CH3, and this MgBr is the counter ion which is present like this. And in next step we have this HBr, and if we have this HBr, and the product that you will get, this would be the alcohol we are getting from here, and finally MgBr2. Now next one, in the same way, if you have a carbonyl compound and in presence of sodium borohydride, what would the product in this case? Now again, first of all, this sodium borohydride, if I write like this, H, and this is our this negative charge present over the boron, positive charge is present over the this. So here this hydride ion will attack over this electrophilic center, and what you will get, O minus, and this is our hydride, hydrogen is attached over here. BH3 is removed from here. One of this counter ion, that is Na plus, which is present like this. In next step, the workup will take place, and in presence of this aqueous acid, so this will take H plus, chloride ion will get removed, and finally you will get this alcohol as a product plus, and this is this NaCl, which is formed finally in this reaction. Okay, so these are the two examples. In the same way, we may do the reaction with other. Suppose if you have carbonyl and in presence of NaOH, we may do the reaction, and suppose this one, and so what would the product in this case you want to write? So in the same way, we may do the reaction in presence of, suppose if we have sodium ethoxide, or sodium methoxide is there in presence of so in the same way, the product, that final product, the final product would be here you will have this OH, and here you will have this OH, and this hydrate, we are getting this hydrate over here, and here the product which is formed is the hemiacetal is the product which is formed. So these are some of the examples for this these carbonyl compounds, and in next lecture I will discuss the formation of hydrates in presence, that is the acid catalyzed and basic catalyzed reaction, and the formation of acetal, that is hemiacetal, or this hemiketal